Good afternoon, and welcome to this week's joint Heidelberg Astronomical Colloquium. And with great pleasure, I welcome Fabian Schneider, who will talk to us about, or explain to us how stars and which stars do form black holes, which obviously is of great relevance in binary systems for the gravitational wave experiments that are available now for quite some time. So before we get to the scientific topic, let me quickly introduce the speaker. Fabian got his degree from the University of Bonn, where he worked together with Norbert Langer in 2015. He has had quite a number of very prestigious awards and fellowships. It starts with the Studiendetector des Deutschen Volkes, which is very difficult to get and it's very good to have during your studies. He then went to Oxford and was holding the research fellowship and a postdoctoral research fellowship from Christchurch College. So you got it all, the Oxford experience. After that, he moved to Heidelberg, back to Germany, where he got the Galactic Research Fellowship, which he only held very briefly, because then at the same time, in 2020, he got the Neutron Research Group Awards from the German Science Foundation and the ERC starting grant from the European Research Council. And here to the side, you took the ERC award, which I would also have taken. And he is now working at HITS and at the same time here at the Center for Astronomy, and he is group leader of permanent then-at-track position at HITS. All right. So, Fabian, please tell us about black holes.
Okay, thank you very much. And this is a extremely pleasant introduction, and I feel completely flattered. I hope that you can't see my red flushing face now on Zoom. I hope the audio now works a little bit better, because there were some hiccups earlier with the microphone that Ralph used, but I think this is now going to be better also for the online audience. So thanks a lot for the introduction. It's a great pleasure to be here. And as Ralph said, I'm going to talk to you today about how, which stars form black holes, also in parts how they do this. But if you're more interested in which stars form neutron stars, then please stay here, because I'm going to explain that also to you. If you're more interested in which stars are going to explode in supernovae, also please just stay here, because the questions obviously are all connected. Supernova explosions and everything else is obviously an important ingredient in when we try to understand the entire universe. Think about chemical enrichment, think about the feedback of stars, do think about transient multi-messenger astronomy, and in all of this, which stars explode is an essential question. But today I'm not going to talk about these topics. This is for another day. But instead, I would like to look into what we call the stellar graveyard. And this is a stellar graveyard, as we can see from electromagnetic probes. So here I've shown, or this is a sort of infamous or famous plot that you probably have seen many times, neutron star mass measurements from binary systems containing at least one neutron star in our own galactic neighborhood, and also electromagnetic measurements of black holes in our own neighborhood, mostly coming from X-ray binaries in this case. There are also now some black holes found in binary systems that are X-ray quiet. These two systems have been found by spectroscopic surveys, and the Gaia mission is going to add, and the hopes are high that Gaia is going to add many more black holes that have been undetected so far around stars. But these are the first two systems that have been confirmed, and this is also thanks to our colleagues up the mountain at the Max Planck Institute. You might have noticed immediately something on this diagram, and that is a lack of black holes in our nearby galactic systems beyond, let's say, 20 solar masses. And because you have expected already now maybe the landscape of how it looks like with gravitational wave astronomy, then this is the picture that we have now. So these are all the black hole, binary black hole mergers. There are also some neutron star mergers, and also neutron star plus black hole mergers that LIGO and the Virgo Kagra collaborations have measured so far. And they populate now an area, in particular also in Mars, that we do not see in our local neighborhood. I'm going to come back to this question, and hopefully at the end, you're going to understand why that is the case. You might have also noticed that there is what in the back days, sort of people called a neutron star black hole mass gap, but clearly you can see a couple of points in this gap. So don't consider this as a gap, but maybe rather like a dearth or something like that. If you're only going to look now into the data that is available from gravitational wave astronomy, then you have data of about 80 binary black hole mergers. And what you can most easily determine from such merger systems is the so-called chirp mass. The chirp mass is a combination of the two black hole masses involved. It looks a little bit like a reduced mass, but not exactly. So you have slightly different exponents in this expression. If you have an equal mass merger, then the chirp mass is just about 90% of one of the two objects involved. And the only thing I would like to pay attention to now is the upper plot, where you have in these thin gray lines the observed, observationally inferred probability density functions of each individual measurement that LIGO has and the detectors have seen so far. And there are clearly a couple of features that do stand out. And this is sort of what is absolutely fascinating now, that we can try to do science with this. Let me highlight a couple of things. First of all, there is a gap in the chirp mass distribution as observed today. This gap is at about 10 to 12 solar masses. And you can also immediately see, so this is the direct observational data down here. This is an inferred distribution for what is the underlying distribution if you take into account some of the biases that the detectors have. But you can immediately see there are some features, and I've just highlighted some of them. There's a feature here at around chirp masses of 8 solar masses, something at 14, something at 27, and there's even some report of some feature or hump or whatever you want to call this at this high mass end at chirp masses of about 45. This corresponds also to black hole masses. Here from the first thing of about 9 solar masses. For the second feature beyond this chirp mass gap, that corresponds to black hole masses of 16 solar masses. And I want you to keep these masses sort of in your mind, and I'm trying to explain to you why this might be the picture that we can expect from stellar evolution. I should say at this point, we are still dealing with low number statistics. Yeah, we have 80 measurements, but this is yet a little bit of low number statistics. So there are different groups that try to assess now the significance of all the features that we have observed here already. Some of the features appear to be significant. For example, this big peak at 8 or 9 solar masses, and also this huge peak over here at 30 solar masses or so. This appears to be significant, and the rest is still debated. However, LIGO and the campaigns are just continuing their observation runs. So in a couple of years, or maybe even at the end of this year, we'll know much better how this looks like. So I'm trying to explain to you what we can do with this today, and what we can maybe learn already from the data that we have. I'm going to start with plain single stars. And I'm really starting at the basics, sort of back to our stars 101 to explain a couple of concepts here. This is a Hertzsprung-Russell diagram of an initially 13 solar mass star. And you can observe its evolution starting on the main sequence where you burn hydrogen in the center, and then the star crosses the Hertzsprung-Russell diagram, becomes a red supergiant. It climbs the giant branch, does core helium burning at this location, and then further climbs in luminosity until it hits its final end point in this Hertzsprung-Russell diagram and explodes here in a core collapse supernova. All I want you to take away from this is, if you look into the star on the main sequence, there's a little dot that has appeared. And on the red supergiant branch, the star will have to scale such a size. Yeah? Just remember, stars are growing while they're aging. This is going to be relevant in a moment. If you look only at the surface of a star, we will never understand what's going on in the center and which stars are going to explode and form black holes, which is why let's turn away from the surface and look into how the core of a star is going to evolve. And this is stellar evolution in a nutshell. You don't need to know really much more than this diagram. What we're looking into is a sphere of gas that constantly contracts because of gravitation, because of gravity. And inside our star, we have pressure forces that are going to balance gravity. When the star contracts, it's going to heat up. And this is what you observe now in this diagram. So you look into the central temperature of a star versus the central density. And let's just pick one of these lines. Maybe, for example, here, this blue schematic picture. The star in the center is going to contract, and then it can reach conditions, high enough temperatures, so that hydrogen burning can ignite. And then you have a long-lasting stage where there is an internal pressure force that can stabilize the star against gravity, and the star is going to live for a long time in this regime. until this hydrogen fuel is being consumed. The star keeps contracting, well, ignites then at some point helium. Yeah, and it can again contract, ignite carbon, and then so on and so forth. It can go through all the different burning stages: carbon burning, core neon burning, oxygen burning, silicon burning, until you form an iron core. And from fusion and also from fission of iron, you cannot get any energy out. So what's going to happen? This is the endpoint of our stellar evolution. If this iron core then exceeds its effective Chandrasekhar mass, and if it hits then maybe additional instabilities in this diagram, this is the beginning of the collapse of the core of such a star, and maybe we get a neutron star or a black hole out of this. I would like to point your attention to another interesting phenomenon that can happen in stars, and that is if you go to a more massive star, then such stars evolve at higher temperatures. And such an object can evolve in this diagram into a regime here, which is denoted as electron-positron pairs. And so the star becomes so hot in its interior that you can spontaneously produce electron-positron pairs. This takes away radiation pressure support of your star, and the star starts to implode and it's going to collapse. This collapse now, in turn, triggers a thermonuclear runaway. You have thermonuclear runaway burning of oxygen. And so the entire star can explode in principle. And this is what people know as pair-instability supernova. And people have been looking for such pair-instability supernovae for, I don't know how long. But maybe just a couple of days ago, there was a paper on AstroPH. Maybe there's finally this best candidate of a system that has exploded in such an explosion. What we then also teach students in lectures is how this translates into the landscape of neutron star and black hole formation. And this is a plot that is already 2 decades old. So from Alex Heger, Stan Woosley, and collaborators. And you're looking into the metallicity of stars versus the initial mass of these objects. And you can see in different colors where the different neutron star black hole formation regions are. This is only schematically, but this is a summary. Let's pick any range here. And then you would say, well, between 9 and 25 solar masses, you form neutron stars. If you go ahead a little bit higher, between 25 and maybe 40 solar masses or so, the star triggers a supernova explosion, but the supernova explosion is weak. And instead what you get is fallback accretion onto your proto-neutron star, and then you get a black hole out in the center. So this is this reddish corner. And then if you're maybe beyond 40 solar masses, initial masses, then you form directly a black hole from direct collapse. So this is a picture that we usually teach in lectures. There are 2 interesting corners. Imagine you go to extremely high metallicity, then the stellar winds are going to be much, much stronger. So your star sheds most of its mass, and then there will be a threshold metallicity beyond which black hole formation is simply impossible. Yeah, so that's also an interesting insight that you can immediately gain from such a diagram. And then, as I already mentioned, if you go to very low metallicity, then the winds are weak and you can keep a lot of mass. You can grow a large core in a star that becomes hot and then undergoes this pair-instability supernova regime. And this can leave or give rise to a region in initial masses where you don't see any remnant at all, meaning also you do not see a black hole here. So you expect maybe a gap in the black hole distribution. I would like to say, well, this is the original pair-instability black hole mass gap that has been in the literature for a long time. And there's a lot of work going on in trying to determine what are the physical ingredients now that set the pair-instability mass gap. And this is just one of the uncertainties, a beautiful paper here telling you if you modify one of the nuclear reactions during core helium burning on how this black hole mass gap from pair-instability supernova can then maybe change and vary. I'm not going to go into details in this at all in this talk. Instead, I would like to go back to stars that do sort of the normal core collapse supernova. And I'm plotting now in single stars the iron core mass that such objects produce at the end of the evolution when the core starts to collapse. And this is plotted here as the core mass of our stars measured by the carbon-oxygen core mass, but just think about this as a core mass of your object. And you can see that this landscape is non-monotonic. Okay, so it's not like that you go to higher mass stars and then this landscape just increases in iron core mass. Yeah, and all these objects have reached their effective Chandrasekhar mass and then started to explode. And so the effective Chandrasekhar mass here must have been a little bit higher than, for example, over here, and even higher maybe at this carbon-oxygen core masses. Most often in the literature, we do not look at the iron core masses, but instead what people have introduced is a so-called compactness parameter. It is a quantity that summarizes the stellar structure in its center. Yeah, just view it as a summary quantity for stellar structure at core collapse. And you can see that this iron core mass, let me just switch maybe back and forth. Yeah, you can see that this iron core mass landscape translates directly into this compactness landscape. And the compactness parameter is just you measure at a certain mass coordinate inside your star, the radius that you have, and you take a ratio of these two, and this is your dimensionless compactness parameter. I'm going to describe now the stellar structure at core collapse pretty much in this compactness parameter, and just view it as I said, as a summary proxy for what is going to happen. What you can maybe also think about this compactness parameter is the following. There can be a critical compactness beyond which stars are so dense, maybe have so high iron core masses, that it's difficult to explode, and maybe they tend rather to form than black holes. This is sort of up here with the high compactnesses, and maybe they form the neutron stars if you're below this threshold. I've just sort of introduced a threshold that has been used in the literature quite recently, so you can get an idea of how maybe to tell whether a star is going to explode. What you probably have noticed already is that in this landscape, you have an increased compactness at specific core masses of 7.5 solar masses roughly here, and you have generally high compactness beyond core masses of 13 solar masses. And do keep these numbers in mind, because they're going to come back all the time throughout this talk. How this develops exactly in the stellar interior is complex, complicated, but the short answer is the following. The late burning stages of stars are neutrino dominated. And when neutrino losses completely overcome the energy generation from carbon burning, then this compactness goes up, and this is indicated by this gray background. So everything that has a gray background simply means neutrino losses take away all the energy from carbon burning, which also means that carbon burning, which usually proceeds under convective conditions, now proceeds under radiative conditions. And this changes how the core in the center of a star is going to grow. And what it does here, it leads to high compactness. A same or similar phenomenon occurs then for the second increase in compactness, but this time neutrinos are even so greedy, if you like, that they take also all the energy away from neon burning, and so also neon burning in the center turns from convective into radiative, and you see an increase in this compactness landscape. Yeah? So this is nuclear physics, neutrino physics going on in the center in late burning stages of stars, which determines this landscape. And this compactness pattern is relatively insensitive to what kind of stars you're looking into. I'm showing you now single stars at a different metallicity, tenths of solar, and the compactness landscape is pretty much the same. It doesn't really change much. There are tiny details, but I'm not going to go into those now for this talk. What we would like to understand, of course, is how does this compactness now, or the structure that we have in our star, translates into does a star explode or not? The leading idea on how our core collapse supernovae work is this delayed neutrino mechanism. And I just want to give you a brief kind of an idea for how this is supposed to work. So the collapse of our core is triggered because we have reached the effective Chandrasekhar mass. We have an iron core that's larger than that. And so the inner core collapses. So we have an iron core of size roughly of Earth that is going to collapse into a size of a typical city, and that releases gravitational energy. There's a lot of gravitational energy, but most of that gravitational energy is being radiated away again in neutrinos, 99% or so. And this has been beautifully confirmed in the supernova 1987A, where you could observe this neutrino burst here on Earth. So the question now that is puzzling many scientists for a long time, how can these neutrinos explode your star? The problem is the following. The core collapses. You reach densities in the center of your star that are close to the atomic densities, nuclear densities. The strong force takes over, so the collapse is stopped when you form this proto-neutron star. And this produces a bounce, a reverse bounce, a reverse shock. This reverse shock, however, is going to dissociate all the chemical elements that you have produced in nuclear burning and then stalls. And here's a simulation of what this stalled shock is going to do, because you're now still constantly neutronizing the core, and you release neutrinos. And these neutrinos, they can reach, can heat a region which is usually called the gain region behind this stalled shock, and then can lead to this convective fluid motions. And if you have heated, so to say, the region behind this shock enough, and you can overcome this infall process, then the star is going to explode and maybe produce a neutron star and not collapse into a black hole. So this is a simulation where this process has worked out. And I think the consensus nowadays in the field is that they have an idea of how this mechanism indeed works, but they have still a little bit difficulties in reaching the same energies that have been observed, explosion energies in supernovae, but this well, they're confident that this is a process that works out. Obviously, we cannot do such complicated simulations for all our stellar structure simulations to see whether a star is going to explode or not. So instead, what we have to do is we have to go to more simplified explosion models. And here I'm going to show you now for the rest of the talk results that we have gained with a semi-analytic neutrinon supernova code that Bernhard Müller and collaborators have developed. This code is trying to take all the physics that people have learned over the last decades or so in this core collapse business, trying to put this into a simple formula, if you like, to understand how this explosion might work with a given stellar structure that we have. And so we can take our models now and work them through this supernova code and explode our models within this neutrino-driven paradigm. This is what comes out. And I'm going to show you here not only the compact remnant masses, neutron star masses are down here, but well, I want to focus on the black holes as my initial title suggested. So I'm going to spend most time now talking about the black holes up here. You see, and I'm showing this now as a function of the initial mass of the stars, that there's an island here of black hole formation. And this black hole formation corresponds to exactly this high compactness that we have seen already previously. Yeah. And then you have black hole formation again beyond some initial mass. And this is, well, as you was expecting already, this is black hole formation again because we have reached high compactness in the centers of our stars. So if you want to refine then from such a diagram the picture that I was showing you earlier for single stars, well then maybe in this regime of 20 to 25 solar masses, well, this is maybe where you form black holes from this compactness peak. Then in this intermediate range, you can see here there are a couple of gray boxes. This is where from the supernova code, we expect fallback to occur. So in some models, fallback is going to occur and then convert a neutron star into a black hole. In some, it isn't. So there's some fallback black holes that you're going to form. Here, this is just neutron stars, but they might just appear up here as black holes. And then beyond 35 solar masses or so in the single star picture, everything goes directly into collapse of a black hole. So this is, if you like, a refinement of the picture that you have seen before. And I would also like to demonstrate now that if you play the same game at this lower metallicity, the landscape looks pretty much the same. Also for the same initial masses, you form this compactness peak black holes. And then also for the same, let's say 35 solar masses or so, you again go into black hole formation. What you notice is maybe that the black hole masses themselves are going to be a little bit different. And at lower metallicity, you tend to form obviously more massive black holes simply again because you have weaker winds in such a domain. And you might wonder rightly, can we maybe even observe some of that? And yes, you can. And I would like to in particular highlight now some work that a master's student in our group, Teresa Temay, has done. And she looked into where do stars end their life in the Hertzsprung-Russell diagram. So this is a Hertzsprung-Russell diagram and indicated now where all the different models that she and we also in our group have ended their life. The star symbols just indicates, well, an explosion. Black hole formation is indicated by these circles with a black ring. And what you observe again, you have explosions, well, collapse into black holes. This is again our compactness peak, and then explosions over here and maybe collapse up there in the Hertzsprung-Russell diagram. Interestingly enough, and this has been known for a long time, of course, that if you look into the stage of stars at core collapse, there is a close core mass luminosity relation for such objects, similar to core mass luminosity relations of red giants in lower mass stars. And so that means these compactness peaks that we have seen, they are at fixed carbon-oxygen core mass because they're determined by neutrino physics. And via such a relation, that means these objects that fall into the compactness peak, they're always going to appear at pretty much the same luminosities. So a prediction of these models is that you should find maybe black hole formation from the compactness peak black holes at this point in the Hertzsprung-Russell diagram. And there is one candidate star that simply disappeared from view. And this progenitor star that has disappeared has this beautiful telephone number over here. Underwent a little outburst in 2009, but this was not a supernova explosion. But ever since has disappeared. And the best model so far is that the star collapsed into a black hole. You could measure, or these people could measure the luminosity of the star, and this puts it exactly spot on at this luminosity where we would expect black hole formation from the compactness peak. So this is a beautiful maybe support for what I'm explaining to you, but bear in mind, determining luminosities from such pre-supernova stars is a difficult business. Okay. So far, I've only talked to you about single stars. But if you want to discuss gravitational wave sources, well, we have to get away from single stars and talk about binary systems. And this is really where things now get a little bit complicated. This is a little animation, again, for you to appreciate what happens in a binary star system. So these are two massive stars. And now recall what I mentioned in the beginning of this talk. Stars grow in size as they age. And so the more massive star, the whitish object, now has grown in size. And at some point, its outer layers are going to be gravitationally transferred simply onto the companion. And this is the phase of mass transfer. And in this phase of mass transfer, this star is going to lose now most or all of its hydrogen envelope. The only thing that is then left of such an object is its helium core. And the star at some point here is then going to explode in a supernova. And this will be then of a type 1bc supernova, as you maybe would have expected, given for a star that has lost its hydrogen envelope. The other star has gained mass. Yeah, so it's also not necessarily going to be just a normal single star, and has gained a little bit of mass, and also later on is going to explode. Binary stars in general are incredibly common in massive stars that undergo supernova explosions. And so this is from our 2012 work. We've been showing that about 2/3 of all the massive O stars in the galaxy, at least, are going to undergo some sort of binary mass exchange. I would like to point out this envelope stripping, which you have seen just in this animation. But also I would like to sort of highlight here that about a quarter of the stars are expected not to sort of do a stable mass transfer, as you have seen in this movie, but maybe even merge and form one star. Let me go back into this diagram that I have just, or this animation, and just put this into still images. So we started out with two massive stars, and we have seen in this animation this first phase of mass transfer. In this phase of mass transfer, this star has lost its hydrogen envelope, and you form a helium core, or helium star, and this helium star is going to explode. So this is a supernova from a binary stripped star. Later on, also the second star here that has accreted a little bit of mass is going to evolve. It's going to increase its radius. Maybe some of its wind is being accreted by this compact object, and you might see it as a high mass X-ray binary. In such a high mass X-ray binary, mass transfer, once it sets in, is going to be unstable, and you form here in this cartoon what is known as a common envelope phase. So this high mass star is going to engulf its compact companion, and again, in such an event, what you do is you lose the envelope of this massive star, and you're left with a binary stripped object again that is going to explode in a supernova and form the second compact object in this binary system. Once you have such two compact objects, in this thing now, two neutron stars, could also be two black holes, where they can radiate gravitational waves and then finally merge to form one black hole that we have seen in LIGO. If you only modify the initial conditions here a little bit, for example, pick a lower mass companion, maybe put it into a somewhat wider orbit or so, then this first phase of mass transfer is not going to be stable, as I have depicted in this animation before, but you go immediately straight into a common envelope phase. You lose the envelope, you have a supernova from a binary stripped star, and a companion that can maybe initiate mass transfer. You might see it as a low mass X-ray binary in this case, because the companion is of lower mass. Well, and this lower mass companion, let's assume, is going to form a white dwarf and not a neutron star because it can't explode. Okay, so this is how such a system would form. And maybe for completeness, if you start out yet a little bit different in the beginning, then these stars might actually go into a contact configuration, touch, merge to form one object. There's a high chance that you produce strong magnetic fields in this merging phase, and when such an object then either explodes, maybe this even gives rise to magnetars or so, highly magnetized neutron stars, or then to a black hole from a star that has merged previously in its evolution. Oh yeah, so I was picking a binary systems here where the supernova is not disrupting the binary system. So yes, the more you go down this path, the rarer and rarer sort of such systems become. Most of them are going to just unbind from the supernova explosion. Yeah, exactly. I want to make a different point from this diagram and from this kind of brief overview of what binary stars do. If you look into the stellar graveyard, all the masses that you have determined, the masses of the neutron star from double neutron star systems and neutron stars plus white dwarf systems, the X-ray binaries that give you the black hole masses of these electromagnetic sources, and also, of course, all these merging objects here from LIGO, all these compact objects derive from stars here, here, and over there, from stars that have lost their hydrogen envelope in a binary mass transfer phase. So if you want to understand the black holes of these guys, you've got to understand what binary evolution does to your stars. And it's been known since, well, let's say 25 years or maybe even longer, that this envelope removal is going to affect the core structure of the stars. I'm not going to go into details on how this works out, but I just want to give you a taste here of a tulips visualization that my postdoc Eva Laplace has made. And it illustrates how a single star would look like at the end of core oxygen burning, and a binary strip star that has the same core mass as a single star. And I think just from visual inspection, you can observe that the burning layers and the intensity of the burning layers of all the different layers here is quite different in these two objects. So you form cores that are different and unlike of normal single stars, and that you can actually not reach in standard single star evolution. And how does it pan out? Again, if you look into this compactness landscape, yeah, this is what we've looked into in the beginning. This is for our single stars. And this is now how this binary strip stars look like. So surprisingly, again, the compactness landscape is quite similar, though there's a systematic shift. And the systematic shift might not look a lot here to you, but it has quite significant implications, as I'm going to show you in a moment. And again, I would like to mention these compactness increases, compactness peak here and high compactness over there, that again occurs at pretty much similar carbon and oxygen core masses. Yeah, for single stars at different metallicities, and now even for binary strip stars, it's not so different here. You can also go at lower metallicities, and you'll find the same picture. Blue is single stars, red are our binary stripped objects. Again, same story here. So if you want to take something away from this, then there are characteristic carbon-oxygen core masses where you get high compactness, and most likely then also black hole formation in all sorts of stars, no matter what their history was. If you translate this now into black hole masses, again with the same code that I have described earlier, then again, just pay maybe attention to the higher mass part here. You'll find again this island of black hole formation, but now in the stripped stars, this is at a different initial mass because you have a different relation now from your carbon-oxygen core mass to what the initial mass of a star was in the past. And I think you see the elephant in the room here already. And this is the slight shift in the core masses of our stars that leads to a tremendously different initial mass range over which you form neutron stars or vice versa black holes in stripped binary objects. So in single stars, yeah, I told you, well, maybe in initial masses less than 35 solar masses or so, you're going to form most likely neutron stars, and beyond that black holes. For binary stripped stars, this is now 70 solar masses or so. Yeah, this has quite some implications in a moment. You also observe this neutron star black hole mass gap. Although in these models, when we don't consider the fallback, this neutron star black hole mass gap comes out naturally at a range of 2 to 9 solar masses. If you make some assumptions on what the black hole fallback is exactly, you can easily explain this gap or dearth at 2 to 5 solar mass that I mentioned earlier. No problem, but it tells you this dearth that you observe is most likely connected to fallback happening in supernova explosions. So it's, I think, beautiful to understand how this can come together. Also, remember, the maximum black hole mass that we have seen in the galaxy, Cygnus X1, was about 21 solar masses. If you look into the black hole masses that you get from our binary stripped stars, none of them reaches values in excess of that. And so the maximum mass that we observe in this Cygnus X1 is most likely simply a consequence of that the black hole originated from a star that has lost its hydrogen envelope, so it's going to naturally have relatively low black hole mass. Yeah, so it's a binary evolution again that describes this. There are some more implications for from the subbinary stars, for example. They exploded with higher explosion energy. Is also interesting to know, but maybe not so interesting now for us. What I would like to point out is that because of this binary strip stars, you produce neutron stars now of a much larger initial mass range. You remove black hole formation. And if you were to incorporate this in current day population synthesis works that try to predict the gravitational wave sources, this would imply a reduction in the black hole merger rates of 80–90%. This is unaccounted for in any of these population works so far. You can also make histograms and mass distributions of the black hole masses. And here comes the big surprise, or maybe not such a big surprise, but a very interesting insight. So if you convert now your stellar population, take some birth configurations, you can produce such mass functions. And the first thing, maybe we look into the single stars, which is the top pane here. You observe again, you get this compactness peak from this characteristic carbon-oxygen core mass driven by neutrinos in the evolution. You get a gap in this black hole mass distribution, and then again, you do get black hole formation. Here is sort of a contribution of our fallback systems. Do take into account or be warned that there is this hatched area which says LBV phase. A huge uncertainty in our understanding of stellar evolution. These objects are going to evolve through a luminous blue variable phase, and we don't know how much mass they're going to lose. It might be that an instability kicks in and removes the entire hydrogen envelope, in which case all of these objects would behave as effectively as binary stripped stars and then produce black holes more alike this distribution. But we don't know at the moment, and this is a big uncertainty here. In the black hole mass distribution for the binary stripped stars, you again have this compactness peak, you have a contribution from higher mass black holes and the gap. So we predict a bimodal black hole mass distribution here. And the clue and the interesting part now is, regardless of what the metallicity is, solar metallicity or a tenth of solar metallicity, the first peak from the compactness peak, the gap, and then also the high mass black holes are only mildly sensitive to metallicity and actually are greatly independent of what the metallicity is. So from these binary stripped stars, you predict characteristic black hole masses of around, let's say, 9 solar masses here and 16 solar masses up there, and sort of no black holes in between. Why do you do this? These masses where stars collapse into a black hole is connected to the characteristic carbon-oxygen core masses that I mentioned. And in stripped binary stars, you have a direct relation between the core mass of a star at core collapse to its total mass. And this relation does not depend much on metallicity. Okay, so I mentioned these characteristic black hole masses already. And this is the point where I would like to go back to our picture that we got from gravitational wave astronomy in the beginning. Remember, these are these chirp mass distributions, the pure data that has been found so far. There is this gap in chirp masses at 10 to 12 solar masses, and two features that I'm now just going to highlight sort of at 8 and 14 solar masses. And you already see where I'm going to take this picture to. Well, these characteristic black hole masses that I described from binary stripped stars, they would add contributions exactly to the left of this chirp mass gap and to the right of this chirp mass gap. Yeah, so this might be an explanation of why such a feature is being observed today in the gravitational wave data. You can, of course, also merge a 9 and a 16 solar mass black hole before someone is going to ask. That could get a contribution into this gap region that has been observed. And in fact, we would predict such systems to exist, but they will be suppressed by binary star evolution. I'm not going to go into the details now. We can maybe discuss later, maybe also in person, but this is a little bit an involved argument. Yeah. Maybe it's also interesting to look at the very high mass end here, because is there a cutoff because of pair instability supernovae? Unfortunately, the data is apparently still a little bit inclusive. So there is no final answer maybe to this question. So we have to wait maybe a bit longer, but I think the current evidence would rather point towards the fact that there is maybe none cutoff in this distribution. And if that was the case, well, you've seen that you can play with some of the nuclear reaction rates in stellar evolution, and you can move this pair instability mass gap. So if in the future you can constrain and have more measurements of black holes in this high mass regime, you might have a handle on directly measuring or constraining or putting constraints at least on such nuclear reaction rates. And there are more physical ingredients in there. By the way, you can do the same with these characteristic black hole masses that we have predicted from binary star evolution, from binary stripped star evolution, because here also the core masses, they depend on this characteristic carbon-oxygen core masses, and they are inherently linked to nuclear physics, neutrino losses, and some other processes. So if this picture that I'm painting here is correct, then you could use such observations in the future, even again, to put constraints on this. And so this is what I would like you to take away from this. So there are these peaks and gaps, and we still have to wait how significant they are, and maybe we are going to be in trouble, or maybe the supernova people are going to be in trouble at some point. But if this persists and this picture continues to emerge like it does so far, at least over the different observing runs, then this can be used, for example, to constrain late stellar evolution. It might be able to constrain supernova explosion physics. And what I haven't mentioned yet is you could even use this to measure cosmological expansion. The point is, usually when you observe chirp masses, you observe chirp masses with a factor of the 1 plus z, sort of the redshift evolution. And you need to disentangle these two signals. So what is the chirp mass and what is the redshift evolution? But if you know that in your black hole mass distribution, for example, there are some characteristic uniform features that you should expect at all the different redshifts, then you can statistically disentangle this and make direct measurements of cosmological expansion. You can do the same, by the way, with this gap from the pan-stability supernova, if it exists and if you can measure it. But this is future work on this front. Okay, so I think I probably have maybe 5 or 10 minutes more. That's great because that allows me to talk yet about a different topic. So we've been discussing what kind of black holes do you expect from single star evolution. We discussed what do you expect from binary stripped star evolution. And I already alluded a couple of times to this, so maybe mergers and things, they can also do interesting things in terms of stellar evolution. And in particular, I would like to pay a little bit of attention to the most massive black holes that you can maybe form in stars. And maybe this journey starts with this impossible black hole that has been detected by LIGO, GW 190521. This was a merger of two black holes where both individual sources were 85 solar masses and maybe 66 solar masses. There are quite big uncertainties still on these numbers. But both of these masses could potentially be within the pan-stability supernova mass gap. Well, and that's at least from single star evolution shouldn't be possible. You should not get a black hole in this gap because these objects should have exploded. So the question is, how can you form such massive black holes? Is the pan-stability supernova gap really at these masses? So many questions that are interesting that you can ask. There are a couple of references here if you want to dive a little bit deeper into these questions. There's, of course, a very simple solution to the problem. Well, what if both of these black holes are second-generation black holes? So that each of these two black holes have already experienced at least one merger in the past. Well, then you can easily just populate this black hole pan-stability mass gap. So I would maybe just not discuss this solution now, which is, of course, a possible solution. And this last paper here from 2023 from Gamba et al., they even find evidence that this black hole merger here was maybe in a hyperbolic orbit, so it might have been a capture in a dense stellar environment. So that's what they claim. But anyhow, let's still talk about the question, so what is the maximum black hole mass that we might expect from stellar evolution at a finite or high metallicity? I think this question is quite interesting on its own. And the solution to this question is going to come from 1987A and stellar mergers. This is just a little illustration of two massive main sequence stars that are going to merge and form one object so that we can understand what is happening in such events. And it might sound a little bit surprising, but sort of combining these two, and we can actually get quite massive black holes. And I'm going to explain to you how you do this. This is the picture now. If you take two main sequence stars, a little bit different masses, but they have some hydrogen in the center, but some of that hydrogen has been converted already into helium. And if you merge these two stars, and this is also what this animation that I've shown earlier is going to have shown to you, is you form an even more massive star. And most likely this more massive star can now adjust its structure. We're going to get a larger convective core on the main sequence. And what you would get out of such a merger is what you know maybe as a classical rejuvenated blue straggler star. And this is then also illustrated here in this Hertzsprung-Russell diagram. We start again with our 13 solar mass star, and we have different mergers, and how much mass has sort of been added to our star, or how much mass was involved in this entire merging process, is being given here in color. Don't look into the details. I think for now, the important message that I want to carry over is here this merger happens towards the end of the main sequence evolution, but you can have picked a different time. And then depending on how much mass you add, the star is going to be much more luminous. Let's maybe, I don't know, pick this line over here. So then you would have a blue straggler that then continues its evolution here on the main sequence, but the evolution is pretty much that of a single star, but now with a higher mass. The stars are also then crossing the Hertzsprung-Russell diagram, and then they're going to explode here as red supergiants, or maybe going to collapse into a black hole, again, because the star has reached the characteristic carbon-oxygen core mass to be in this first compactness peak. Same story even for mergers. Just wanted to remind you again about a quarter of the O stars is probably going to go through such merging episodes. when talking about these mergers, in particular now in mergers that involved a post-main sequence star, so a star that has already produced a helium star, there is a layer where you still burn hydrogen into helium, and then you merge such an object with a main sequence star, then the outcome is going to be quite different. And this is some work that a bachelor student in our group, Julian Saling, has been doing quite extensively. And he produced then objects that after the merger have a small helium core, but a relatively large hydrogen mass. And if this core here is small enough, or vice versa, if the envelope after such a merger is big enough, then what can happen is that the star no longer, after such a merging event, crosses the Hertzsprung-Russell diagram to become a red supergiant, but instead it stays hot and forms a blue supergiant. And then such objects would burn helium in their core as blue supergiants, and as you can see, they would even explode as blue supergiants. So why is this interesting, and what is so remarkable about this? This again has to do with stellar winds. The strongest stellar winds that you experience in stars are usually on the red supergiant branch. So these objects here, they experience strong winds and they will lose a lot of mass. In comparison, blue objects closer to the main sequence in this part of the Hertzsprung-Russell diagram, they still have decent and strong winds, but nothing compared to what happens on the red supergiant branch. So that means these objects here, they can retain much higher mass and retain this high mass up to core collapse. There's another elephant in this room that I'm going to explain and talk to you about in a moment. And this is, again, this luminous blue variable phase and Estorados instabilities. So I'm going to show you now two Hertzsprung-Russell diagrams. This is the one that you have seen already. So these are single stars and also all sorts of mergers of stars that occurred while you have two main sequence objects. And this is where they explode in the Hertzsprung-Russell diagram. Supernova 1987A exploded here. So it was a blue supergiant, which was a big surprise because all this sort of single star models would predict a completely different location for such an explosion. If you then play the merger game, so to say, you can produce blue supergiants, and then, well, you can explain actually the explosion side of supernova 1987A and many more details, for example, this ring structure and so on, but there's an expert in the room that you should talk to about this. I want to talk about this elephant, which is called luminous blue variables, and the physics that we don't understand here. If your star enters this region of the Hertzsprung-Russell diagram, observationally, you infer that these stars lose a lot of mass. And again, we don't know how much mass they're going to lose. But it might be that there's an instability that is being triggered, and so that all these objects that evolve for quite some time in this region, they simply lose their entire hydrogen envelope. Well, and then we don't get much massive black holes from that. Yeah, so these blue supergiant solutions, they can come now at a rescue because they, from the first compactness peak here, they predict that some stars explode without having evolved for a long time in this LBV region. So they can retain a lot of mass. And if you look into our models, in particular into these guys over here, so here we get an explosion from our merger models. So then no black hole, unfortunately. But from the first compactness peak, again, carbon-oxygen core masses of about 8 solar masses or so, the stars are going to collapse, and they will not have been subject to the strong LBV wind mass loss, and they will also not have been subject to red supergiant wind mass loss. And then you can get very high black hole masses. And this is now at solar metallicity, I should say. So at solar metallicity here, we can get black hole masses of up to 50 solar masses from these models. And if you then even allow maybe for triple stars or repeated mergers in such unstable triple configurations, you might even go up to 80 solar masses. So definitely within what people have hypothesized to be the pan-stability supernova mass gap. And this, in fact, is also one of the ways that have been invoked already to explain this impossible supernova. The idea, you form a blue supergiant, it has a small core, so it doesn't undergo a pan-stability supernova. It is blue, has a large total mass, so it might not actually be subject to strong wind mass loss, and so it can retain a lot of mass. And so this is the idea that some people have put forward also for these objects. But here's a picture for solar metallicity. You can produce massive black holes. Okay, I'm going to stop here and want to show you a quick summary for maybe the key points, because you want to know ultimately which stars form black holes now after this talk. So I think it is exciting to look into gravitational wave astronomy, and there's so much data coming in. And we can really observe substructure. We can find features. Hopefully the features persist and they're not just low number statistics and Poisson noise. But the hopes are that some of this is going to stay, and then we can probe stellar physics, we can probe supernova explosion physics, and even go beyond that. So this is extremely exciting. Also, to me personally, I'm absolutely excited by all the electromagnetic observations, and in particular now Gaia. I'm literally waiting for the Gaia team to release the information on binary star systems, because there are many people, many groups in the world that are literally waiting for this to be released, and then they could immediately jump onto this and find maybe more black holes in this huge trough of data. In terms of single stars, I've shown you a refined picture compared to what you might be teaching in your Stars 101 lectures, sort of from Alex Seger and collaborators from 2003. The refinements are not so gigantic, I would say, but still significant. I want you to keep in mind there are characteristic core masses in stars driven by neutrino losses and nuclear burning in late stellar evolution that leads probably to black hole formation, and this is at about 7.5 and maybe 13 solar masses roundabout. Yeah, and then you have this non-monotonic black hole formation landscape where from this compactness peak you form maybe black holes in a range from 20 to 25. Then there's a region where you form some black holes from fallback, but other stars might just explode in a supernova. And then initial masses larger than 35, you simply probably collapse directly into black holes. So if this is what you need for your single star picture, I would pick something like that. But then I have shown to you that binary stripped stars and also stellar mergers, actually I didn't talk much about this, but both processes do genuinely change the interior structure of stars, and then you get different kind of conditions at the stage of a supernova. However, you get the same characteristic core masses because this is determined by neutrino physics again, ultimately. In these stripped binary stars, you might have neutron star formation at solar metallicity up to initial masses of 70. So this can change quite a bit. Also, maybe some feedback computations, well, actually not so much. But most importantly, you produce characteristic black hole masses, and this is a prediction from these models at 9 and 16 solar masses, and this gives a bimodal black hole mass distribution, and I have argued that this bimodal black hole mass distribution also should give rise to a bimodal chirp mass distribution with maybe a dearth or something that a gap exactly at the observed location, at least at the moment. So let's see how this how the future is going to go in this direction. So this might explain these observations that you have seen, and from stellar mergers, you can produce blue supergiant structures, and they have the advantage that you have a relatively small core, but yet they can fall into the compactness peak and then collapse into a black hole. But these blue supergiants probably avoid a lot of mass loss from red supergiants and also from luminous blue variables, so they can keep a lot of mass. And this might be a way to form the most massive black holes, at least in the galaxy. But well, there are more ways, as I have explained to you already. Before I'm going to stop, I would like also to thank my incredible team at HITS. So this is the stellar evolution theory team at the moment. Unfortunately, we don't have a group picture for all of us. And there's also the current Klaus Tschira guest professor, Philip Podsiadlowski, who's here in the front. He's going to be here for a couple of months. If you want to talk to him in particular, maybe about 87A, if you have any questions on that, I think he would be the expert sort of to talk to you about. Thank you very much for your attention.
Thanks, Fabian, for this fantastic overview of stellar evolution that goes well beyond stellar evolution 101. I think this is really cool what we have not known about stars. That's what we really discover now. We try to make many of the recent observations which were surprised and understand. So I think this is pretty. I talked a lot about the black hole mass distribution, many of the matter, the spin of these black holes to how they form with the maximum spin. There are differences between single stars and binary stars, which might have a different budget.
So great question. So I hope that the microphone also was able to get this onto Zoom. The question is about spins in, no, okay. So the question was about the spins of these black holes. Yeah. And whether the different scenarios that I was discussing can predict different spins for these objects. I would say, surprisingly, maybe for some people, observations of these gravitational wave sources, they do seem to tell us that these black holes in the binary black hole mergers have, well, not a large spin, actually no spin at all. And this is maybe not so surprising from a stellar evolution point of view, because we know since a long time already that there is a yet unidentified process in the interior of stars that is extremely efficient in transporting angular momentum. This has been observed in astroseismic data of lower mass red giants. This has been observed in the spins of white dwarfs, neutron stars in the galaxy, for example. And yeah, so the question still is out, how do you get this angular momentum transport? But if this is incorporated in such, for example, population synthesis predictions, then also there from all these channels that I was describing, the prediction is that the black holes are spinning rather slowly, which is in line, I think, with what has been observed so far.
Okay, I intersect the question. So I was wondering about the stellar mergers. Because if you merge, you completely reset the stellar structure. Right? So you bring new fuel to the center. What does it tell us about the lifetime or the overall luminosity? I mean, you described it in such a way that it does not change much, except that the star has suddenly more mass, but there must be more to this.
Yes, there's, sorry, I should repeat the question for the online audience. The question that Ralph is asking is the details more or less of the merging process and what determines the real structure, how much mixing do you get in this process. And yes, I've painted a picture that is extremely simple and simplified. And I apologize to everybody who is now telling me off this was too simple. And I am well aware of this. Maybe the easier part is maybe if you merge two main sequence stars, because then, at least from what we understand so far, it seems as if, yes, you just merge the two things and the star can adjust to its final new structure. There is a big if here, and this big if, or this big question mark, I should say, is called semi-convection in some of these stars and the efficiency of that. And you can even, if you look closely into this diagram, you can see that there is one merger model here that spends a lot of time for helium burning in this blue region, because this is a star, although this was a main sequence merger, that has not fully rejuvenated. And so we observe this. And then what it just means is that semi-convection was not efficient enough after the merger to grow to the normal convective core size that such a star would like to have. Now, yeah, and then you have a small core for such a star, and it spends time in the blue part of the Hertzsprung-Russell diagram. The same now in these post-main sequence mergers. My zeroth order merging thing that I described is that you keep this dense helium core. So the merger process here, maybe you can imagine just like buoyancy or so. You have a dense core in one star that is sort of the more less buoyant object that is just going to sink into the center of your star. Maybe not without any mixing, but yes, you can maybe get some of this helium that was here in this merging process and mix it throughout the star. Definitely, this is what people observe if you do more complicated merger simulations. And then the other star here has, of course, the densest material in its center, and then this might mix with the hydrogen shell over here. But ultimately, when you're done, and this is interesting for these things because you ask for the luminosities of these blue supergiants, their structures here, and this is what Julian has also looked into quite extensively, is that the luminosity is given by the luminosity from hydrogen shell burning. So you have a direct relation now between the mass of this envelope and the luminosity of the stars. So the structure here, this is how we described it, sometimes looks like as if you have a helium star and on top you put a new main sequence star. Of course, this new main sequence star will have some chemical composition, which is then determined by exactly these mixing processes that were happening here. And they are difficult to quantify at the moment. And we're trying to obviously figure out how this works out in detail. And then this implies also differences for the structure of these cores at core collapse. But I thought this was maybe going too deep for such a colloquium here.
So the question is, are you able to, or can you expect one day with a semi-analytic code after calibration of a few objects using the full neutrino propagation code for neutrino explosions, etc., to predict the distribution of magnetization and rotation of these objects? This would be extremely interesting for the cosmic ray electron inputs and gamma ray emissions.
Okay, so I think Richard is asking whether we have a magic wand that can solve everything. Of course, I like to be optimistic, and maybe it's at some point in the future, maybe yes, definitely not now. And this is even something I believe that if you do fully fledged 3D collapse simulations is difficult to get. So putting this then also into such a simplified a parametric code. This is maybe a little stretch, but it would of course be great. Maybe if you ask this question in 50 years time or so, maybe this is too pessimistic, maybe 20 years or so, maybe you'll get a more positive answer.
Secure, are they theoretical? Is the theory behind the pair instability supernova? Is that a number very clearly defined now theoretically, or is it still certain theoretical model?
Yes, so the question is, how well theoretically are the predictions for pair instability supernovae? And maybe I can just try to go back. Here we are. It tells you there are huge uncertainties. I think in this is not only for this pair instability supernova mass gap. So the uncertainty that you're looking into here is a nuclear rate uncertainty in the carbon-12 plus alpha reaction that is important in helium burning and later helium burning. And this is just a deviation of this nuclear reaction by 1, 2, or 3 sigma into the different directions. And you already see, I think, that you, for my taste, have a pretty huge sensitivity on where this pair instability supernova mass gap is exactly. This is only one of the nuclear reactions. People have done the same, don't have the reference now on the slide, for more reactions, for example, the triple alpha reaction, helium burning, and this adds another layer of complexity. Then there are people that have looked into what happens if you have a pair instability supernova of a star that has a hydrogen envelope. And then what they have found is that in such cases, you can get a dredge up from the hydrogen that dredges up a lot of helium. And this dredge up in turn depends on how you treat convection and all sorts of things previously in the evolution. So my answer would be there are actually quite significant uncertainties on the predictions here. And I'm well aware that in the past, people have advocated the exact opposite view, saying that this pair instability supernova mass gap is rock solid, and we know it to a precision of point something solar masses. I think this has changed quite considerably over the last couple of years. And I would, if you're interested in this, really recommend this paper by Rob Farmer here, and also more papers that later came out on the same question. I think they're great and tell you actually how I think uncertain this is. And this might even be needed, because if LIGO, the data is correct, that there is no drop-off yet observed for this pair instability mechanism. And I'm convinced that it has to occur, it has to be around. Unless you find some way to lose a lot of mass in this star. So there are ways out, but.
What about metallicity? You went down to a tenth of solar, but if you go to, really the first stars or the second stellar generation, let's say to zero metallicity or 1,000 or 10,000, would this trend that you described remain, or what would you expect?
Mm-hmm. So if you go to absolute rock zero metallicity, I think then the evolution of the stars is going to be quite different. Remember the massive stars, for example, that do hydrogen burning by the CNO cycle. You can't do this at zero metallicity. So you have helium burning plus hydrogen burning operating at the same time at these stars. And so I have not done these computations, but my gut feeling would tell me that this picture that I'm showing you is going to be different there. If you go then to stars that have a little bit of metallicity, where you can then sort of do the normal stellar evolution via the CNO cycle, and you have hydrogen helium burning and so separated well in time, then probably the picture is going to be quite similar. Yes. And there will be differences from the different winds that you have at these metallicities, but if you just go so down, then I guess the assumption is, well, there is no wind. And then you can play this game. So there is a slight metallicity dependence in all of this. So for example, from these stripped stars, you have the second characteristic black hole mass, about 16 solar masses. If you go down to metallicities much lower than this 10th, this would transition to maybe 17, 18 solar masses or so. But it's still sort of, or maybe even this is even 20, but it's still sort of in the same ballpark, I think, what LIGO is going to observe. The picture, however, is different if you go to higher metallicities. Because what you can do at higher metallicities is you remove a lot of mass with the winds. And once you can tap with the wind already into the helium core and maybe in the carbon oxygen core, then of course you're going to change the picture entirely. Yeah, and this is the reason also why it's good that this is actually up here. This is the reason why maybe at some point here you don't form black holes at all, because the winds erode even the carbon oxygen core mass of the stars, and then the picture is different. But at low metallicity it's probably fine, except for zero metallicity.
In the merger calculations that you or others do, what is actually the role of baryon number conservation? For example, in this neutron star merger that LIGO observed in 2017, about 3% of the solar mass was lost. And it is not clear what happens to these baryons because we have baryon number conservation. So how do you account for that in your codes?
Okay, the question is, I'm not sure whether everybody understood this here. This is more for neutron star merger simulations and how this works out in practice. And then the question was about baryon number conservation. The mergers, the stellar mergers that I'm describing here are sort of living stars, if you like, not the compact remnant yet.
Yes.
And in these cases, you don't have any issues with baryon number conservation or so.
That is true, yeah. But
what neutron star mergers are going to do. For the neutron star mergers itself, I'm out of my depth. So if there's someone here in the audience that can answer this question, I would be happy and to hand over the microphone, but I would not know the answer to this.
Okay, thank
Maybe
you.
Christian knows, huh? No. I don't know, maybe Philip wants to chime in or Fritz, I don't know whether you've ever looked into this. No, there does not seem to be an answer here in this audience, unfortunately. So I'm sorry.
That's fine, thanks. But I think there is no answer to this question so far, right?
Yes. Okay, excellent. And with this, let us thank Fabian for a really exciting talk.